Welcome back, everyone. We are to section 5.3. This is a big one, the fundamental theorem of calculus. And I know that sounds very dramatic, but it's actually really important. And we're going to start out by, there's two parts to the theorem. And we're actually I'm going to introduce the whole theorem, the part one and part two, and then we're going to start with part two, and then we'll go back to part one. So let's talk about the area function. The area function looks like this. And what that would look like over here is if we had, so here we have f of t. T in this case is what's referred to as a dummy variable, meaning it's just sort of a placeholder until we can get to the x. And this is the x here. And our area function is this area here. And what's going to happen here is we are going to be integrating incrementally. So it's going to be g of b will look like this, the integral from a to b. So x is our b now, of f of t dt. And then what we're going to do is, here's b again. So g of c is now going to be g of b plus the integral from b to c, f of t dt. And then we're going to further that once again, g of d, our area function, is going to equal g of c, so that's everything to there, plus from c to d of f of t dt. So this is just sort of showing incrementally how we're getting each of these pieces. And you can see we could even break it up even further if we needed to. So let's talk about the fundamental theorem of calculus, part one. This is the whole idea. The people that came up with calculus quickly came to realize that the derivative and antiderivative were connected, even though they each one solved two very different problems. One of them had to do with velocity with the derivative, and the other one had to do with area, which we're looking at now. And the two are actually almost the same but opposite sides of the same coin, sort of. And so the first part of the fundamental theorem of calculus, if we take the derivative of our area function from a to x, we end up with f of x. Meaning the integral and the derivative are opposites. They're inverses of one another, so they actually cancel one another out. The second part of this is, in my opinion, much more useful. In fact, we almost exclusively focus on the second part here for the rest of the semester, and for the rest of Calc 2 and Calc 3. We use a fundamental theorem of calculus, the part 2. And again, we'll come back to the part 1 at the very end here. So if f is a continuous function on a to b, and f is any antiderivative of f, then the integral from a to b of f of x dx is equal to the antiderivative evaluated from a to b. And what that means for us is that this is going to be f of b minus f of a. Meaning once we get the antiderivative, we're going to evaluate it at b and then minus evaluating it at a. So let's exploit this. Here we are. So first I'm going to find the antiderivative, and then we will evaluate it at its boundaries. So this becomes 60 over 2 x squared minus 6 over 3 x to the third, evaluated from 0 to 10. Now, what I'd like to do is I'd like to break them up into smaller pieces. So this becomes 30x squared from 0 to 10 minus 2x cubed from 0 to 10. Many teachers don't do it that way. They'll do the whole thing. So plug in a 10 there and there, minus plugging in a 0 there and there. So this gives us 30 times 10 squared minus 0 squared minus 2 times 10 to the third minus 0 to the third. And obviously the zeros go away. They're gone. And we're going to end up with 30 times 100 minus 2 times 1,000. This is 3,000 minus 2,000, which gives us 1,000. So in terms of area, that would be 1,000 square, whatever the unit is. All right, so for number 2, we want to know the integral from 0 to 2 pi of 3 sine of x. So the antiderivative of that is going to be negative 3 cosine x. Remember, there's an extra negative in there. When you integrate sine. So this gives us negative 3 cosine of 2 pi minus the cosine of 0. Cosine of 2 pi is 1, cosine of 0 is 1, and you can see this whole thing becomes 0. Now let's explore that a little bit. If we do a sine wave, the amplitude's irrelevant. And we look at the graph, we can see that the positive area is exactly the same as the negative area. So the fact that we're getting 0 makes sense. All right, moving on. Let's continue with the second part of the fundamental theorem of calculus. I'm going to rewrite this. That's root t there. And we're going to get, and I'm going to break this up into 2 separate integrals. Now remember, if you can recall, that the square root of t over t, this is t to the 1/2 over t. And remember, you subtract the exponents, you end up with t to the negative 1/2 power. So you can see I broke them up into 2 separate integrals. You don't have to do that. I prefer to do that. This becomes 2 square root of t from 1 over 16 to 1/4. I just did power rule with that, nothing too fancy. Minus the ln, absolute value of t from 1/16 to 1/4. So it goes 2 times square root of 1/4 minus the square root of 1 over 16 minus ln of 1/4. We don't need the absolute value anymore because 1/4 and 1/16 are both positive, minus ln of 1/16. All right, let's clean this up a little. This becomes 1/2 minus 1/4. Minus, and if you remember your log rules, when you're subtracting like that, you can actually take that divided by that. So this becomes the ln of 1/4 over 1/16, which becomes 4. So 1/4 over 1/16. That whole thing becomes 16 over 4, which is just 4. So this becomes, I'll distribute the 2 in, keep it simple. So this is going to be 1 minus 1/2 minus ln of 4. And that's going to give us 1/2 minus ln of 4. Nothing too fancy. Remember, 1/2 minus ln of 4, that's just some crazy decimal number. So there's no functions left when you have a definite integral, meaning you have boundaries on your integral. Also notice no plus c, because the c's actually cancel because you're subtracting. Well, this one's easy. Integral of e to the x is just e to the x from 0 to ln of 8. E to the 0. Remember, anything to the 0 power is equal to 1. And if you remember your log rules, because these are inverses of one another, this just becomes 8. They kind of cancel out. There you go. All right. And on our last page, so we're going to find the area. Now, this is different than just taking the integral. They actually want to know the actual area that's between negative or positive. So we're going to take whatever negative area we have and make it positive. So our final answer, even if it's negative, we're going to state that as positive because they just want to know area. Now, this is a parabola at a vertex at -25. So this is way below the x-axis. And from 2 to 4, you can see when we plug either of them in there, we're getting negative y values. And what that means for us is that means that our area for sure is going to be negative. It's going to be below the x-axis. So at the end, we'll just make it positive. So we'll integrate from 2 to 4, x squared minus 25. And that's going to give us 1/3, 4 to the 3rd minus 2 to the 3rd, minus 25 times 4 minus 2. That's 64 minus 8. (64 minus 8) is 56. Oh. Which is 56 over 3 minus 150 over 3. Getting a common denominator, this becomes negative 94. Oops, negative 94 over 3. And so the area total is 94/3. Now for this second function, what we're going to get, so with the sine wave, we're going to get something a little bit different here. So I'm going to actually draw the sine wave. I'm going to make this pi way over here. Making this pi over 2. And this is at 1, we'll say. So that is going to be negative pi over 2. And that's going to be negative pi over 4. And what's going to happen here is we are going to have here, oh, I forgot to put in the 3 pi over 4. We're peaking here and then we're stopping here. And here is the issue. Here we have negative area. And here we have positive area. And we don't want the area to cancel out because we're actually looking for area. Normally, we don't have to worry about this, but because they're asking for area, we're going to have to kind of pay attention. So I'm going to call this area 1. So area 1 is going to be the integral negative pi over 4 to 0 of sine x dx, which is negative cosine x now this is going to be minus minus, so that becomes plus the cosine of negative pi over 4. Negative pi over 4 is in quadrant 4, and cosine is positive in quadrant 4. So this is going to be, that's going to be negative 1. That's going to be a positive root 2 over 2. Now I want to point out negative 1 plus root 2 divided by 2 is a negative number, as expected, because it's below the x-axis. It's not very much area. So what we're going to have to do is force it to be positive. We'll come to that. So we'll call this A2. It's going to give us negative cosine again from 0 to 3 pi over 4. Once again, this is going to be negative cosine 3 pi over 4. That's become minus minus, so we get plus the cosine of 0. Now 3 pi over 4 is in quadrant 2, and cosine is negative in quadrant 2. So this is actually going to give us a negative negative again. This is going to be a positive root 2 over 2 plus 1. Which means our total area is going to be negative area 1 plus area 2. This is area overall. So it's going to be opposite signs here. So this is going to be 1 minus root 2 over 2 plus root 2 over 2 plus 1. And you can see the root 2 over 2's go away. And we get a total area, the red plus the green, of 2. All right, we're now going back to the first part of the fundamental theorem of calculus. And if you recall, we have this, but we're going to have some small variations on this. For our first one, it's straight up there. We're done. This is just sine squared of x. Done. The second one is a little more involved. So for part 2, I'm actually going to rewrite this. Do you remember we had a rule from the previous lesson that if I want to switch the boundaries, I have to have an extra negative in there? And now it fits with the variable up top. This becomes a negative square root of x squared plus 1. And for this next one, we are going to do a substitution. So I'm going to let u equal x squared, which means du over dx is 2x. And what we're going to end up with, because our theorem says it's just x, when we have some other function of x, we're going to get some extra wackiness going on there. So with that said, we're going to end up with du dx times d over du with the integral from 0 to u cosine t squared dt. And du dx we have, that's 2x. And now we have our piece here. So this has become cosine of u squared. But I'm going to go back, and this is going to become u squared. So here this means that u squared is x to the 4th. So our final answer is there. Some kind of new stuff. We're getting there.